All right, today we get to cover amides and nitriles. Those are the least reactive of the carboxylic acid derivatives, but they're really important. Let's first start with amides, and we'll try to come up with a way to make them. So let's do preparation of amides. Does anybody have a route that they think we could use to make an amide? Yeah, what precursor do we need that's really reactive? Acid halide, right? So the best way to make an amide that we've seen is to use an acid halide, and then if we use an amine, we typically use it in excess because the amine's going to act as your nucleophile and your base. So you need at least 2 equivalents. And when you do this, you can form your amide. Let's make a little note too that this works best with acid halides. You occasionally will see it with anhydrides. You really never see it with esters, just because they're not reactive enough. Let's take a look at an example reaction. It's one of my favorite examples of this. We'll take this compound, which has a funky name. This is called paraphenylene diamine. So it's got 2 amines on it, and we're going to react this with an acid halide. And what do you think we'll get out of this? Do you think it'll be a dimer, or what do you think could happen? Anybody want to throw out a guess? It could maybe form a ring, or it could polymerize, right? It's got 2 sticky ends on both of the molecules, so this could polymerize. And in fact, that's exactly what happens. So if we stick these 2 together, I'll just show one repeating unit, and then we'll bracket it. And here we go. And I'll just put a bracket around here, and this can repeat for hundreds of thousands or millions or billions of units, depending on the reaction conditions. This is a really, really useful polymer. It's called KEVLAR. Are you guys familiar with KEVLAR? Yeah. KEVLAR is pretty fascinating. If you were to measure its strength to weight ratio, it's 5 times stronger than steel. One of the uses is they actually will use it in spacecraft. So the International Space Station is wrapped in KEVLAR. Does anybody know why? Huh?
Because micrometeorites are moving so fast they can puncture a hole in the space station.
Exactly. So all of our satellites are protected usually with KEVLAR because it actually acts like a bulletproof vest for the space station. So if you've got a grain of sand traveling at 20,000 miles an hour, the KEVLAR will at least slow it down, if not catch it completely. So KEVLAR is very useful. It's also great as an insulator, and it's light, which makes it ideal for transportation uses. The other obvious use is bulletproof vests. Oh, let's see if I can open this. I thought this video was fascinating. It shows the power of KEVLAR. Just 1 second. Let me get it going here. So I was reading about the history of KEVLAR, and one of the problems they had with early body armor was that essentially they were asking soldiers to wear steel plates, which is incredibly uncomfortable and obviously not flexible, so soldiers would take them off. But this is one of the newer types of KEVLAR, where they're showing it with different caliber pistols. So that's a .45 caliber. So it only takes a few sheets of this Kevlar to actually stop a bullet.
Yeah, you'd still be you don't have much
Yeah, that was going to bring me to my next point, is oftentimes soldiers, even if they are hit with a round, it will potentially kill them just from the kinetic energy of the bullet, which is why they're trying to come up with new advanced armors that will disperse the energy over a larger area right now. But Kevlar is kind of our tried and true method that we've had around since 1970.
Believe me, plane carriers are heavy.
Yeah, and that's exactly the problem right now, is even the modern armor that's worn in the battlefield, oftentimes the soldiers will be like, oh yeah, I'm going to go out on patrol, and then like a kilometer down the road, they take it out, and they're like, I'm not carrying this is super heavy. So there's actually these new armors that are made of non-Newtonian fluids that are really fascinating. And so they're fluid if you're moving slowly, but as soon as they get hit by a large amount of kinetic energy, they turn into like a solid sheet of plastic, and it will disperse it across your whole chest rather than a concentrated region. So the new body armor is pretty interesting. All right, so let's take a look at the reaction of amides. Actually, I forgot to bring up one other thing. Sorry, I read too much about this morning. Does anybody know why Kevlar is so strong compared to other polymers? Does anybody have an idea? I'll give you guys a hint. Yeah. So these will actually hydrogen bond. So if you guys have taken biochemistry classes and you've talked about beta sheets, right? Beta sheets are these sheets of amino acids. In this case, these form pseudo-beta sheets with one another, and that's what makes them incredibly strong, is not just the fact that they're amide bonds, that they form these two-dimensional sheets of hydrogen bonding. It's incredibly strong. All right, so let's talk about the reactions. The first one is one we've seen already. This is acid catalyzed hydrolysis. So in our pod, we saw that you could take an amide, you could react this with an acid, and this requires a fair amount of heat. But you can convert this into a carboxylic acid. So if you remember our pod where we had our nitrile and we protonated it and we got this amide intermediate and then we continued to hydrolyze it, this is an example of that. Do you guys want to see the mechanism again for review? Yeah, okay, let's go through the mechanism. So anytime we've got an amide and acid around, we could protonate this carbonyl, right? So we saw that in a lot of our previous reactions. And then if you've got water around, this water can now attack into this carbonyl and kick up electrons. Remember, under acidic conditions, you really should avoid showing any negative charges unless it's on a really stable conjugate base. So in this case, we always want to protonate the carbonyl first. Now that we're at this point, we need to do a proton transfer. So I'll just write plus or minus H plus, and we'll move that proton from the water that just added in over to the amine. And now we've got a diol. What's the next step going to be? Yeah, we've got a good leaving group, so we'll clamp down, kick off our ammonia. And then this ammonia can act as a base and deprotonate our carbonyl. I'm showing this reaction with one-way arrows because once you form the carboxylic acid, that's really rock stable, and you're going to have a hard time going in the reverse direction and forming your amide. What if we do want to go in the reverse direction and we want to convert a carboxylic acid into an amide? What do we need to do? So the question is, how can we get from our carboxylic acid all the way back to our starting material? NH3? Not quite. Remember, the carboxylic acid's really stable. It's not going to react with ammonia very easily. What was that? Yeah, make it into an acyl halide first. So if we did want to work backwards, we'd have to first do thionyl chloride, and then we can convert it to our amide by using NH3 in excess. So this isn't a reaction that's traditionally shown with equilibrium arrows because the carboxylic acid's really going to get stuck there. All right, the next reaction, it's closely related, is base catalyzed hydrolysis. Very similar. However, it requires pretty high temperatures. So the first step, we're going to treat this with sodium hydroxide. We're going to crank up the heat. And then we're going to quench this with acid. It's a good thing this does require high temperatures because our whole bodies, all of our proteins, our enzymes are made up of these repeating amide linkages. So we don't want it to be cleaved very easily. However, we can push this in a lab setting, and we can convert this to a carboxylic acid. The mechanism's very straightforward. If we've got hydroxide, this hydroxide can attack into our carbonyl, pick up electrons. Because we're under basic conditions, it's okay to show this oxygen with the negative charge. And then the reason that this reaction is so crummy is that when this clamps down, we're trying to kick off NH2 instead of NH3. That's a really poor leaving group. Whoops. Let's even circle it and make a note. So bad leaving group, which is why this requires a huge amount of heat. And then in the next step, this bad leaving group, which is also a strong base, will grab the proton, form our carboxylate salt. And ammonia, which is why in the second step we need to treat this with acid. So this requires an acid workup if you want to get, your neutral carboxylic acid. Usually you don't see this reaction done in a lab setting because it requires a huge amount of heat and a strong hydroxide base, but you can do it with really, really simple molecules and convert it to a carboxylic acid. The last reaction we're going to see with amides is reduction. So we can take a simple amide and we can convert it to the corresponding amine. So we're reducing that carbonyl group. What reagent do you think we might want to use for a reduction? LAH. LAH is a really strong reducing agent. You need to use it in excess, and then you need to quench this with water at the end. But you can use this to form primary amines. We're actually not going to go through the mechanism for this one. It's a little bit more convoluted, but just remember that in this case, it's one of the only carbonyls where it will actually go past the alcohol all the way to the amine. All right, let's make a little reaction map. This one's going to be a lot easier than our previous ones. Is it okay if I skip pages? Yeah? Some people are still writing. Yep.
H2 and platinum produce that or no?
Yeah, so if you did catalytic hydrogenation with H2 and platinum, you could. It would require really high pressures, though. The type of pressures that most labs wouldn't have the setup to even perform. You'd have to have like a stainless steel reactor. All right, let's do our reaction map. So we said we can convert from an acid chloride to an amide. And then we said we could change this amide into a carboxylic acid. We can change the amide into an amine. And then one we actually didn't talk about, but we're going to talk about next, is changing an amide into a nitrile. But let's hold off on that one. So we've got reaction arrows to connect all of these, and for this top one, going to the carboxylic acid, we actually have two different routes to get there. If we want to go from our acid halide to our amine, we said we needed ammonia, and we needed it in excess, because it's the nucleophile and the base. To go to the carboxylic acid, we said we could do acid and heat, or we could do sodium hydroxide and heat, whoops, followed by an acid workup. We said to get to our amine we needed what? LAH in excess, followed by water. And then to get to our nitrile, we need a reagent we're getting pretty accustomed to, thionyl chloride. And we'll cover that mechanism shortly. So you can tell our reaction maps are getting smaller as we're going along because we're getting to less and less reactive carboxylic acid derivatives.
If we're going to be using acid and heat anyways, why would we use NaOH?
So there might be a situation where you've got a functional group that's sensitive to acid, and in that case your workaround might be to use the strongly basic mechanism. That's a good question. So really either route, it requires a large amount of heat and it's not that popular because of that. All right, let's go to nitriles. We've seen nitriles pretty much all year. There's a few easy ways to make them and one new way. So let's do preparation of nitriles, and let's say I've got this basic, I'm just going to abbreviate this LG for leaving group. And I want to convert this to our nitrile, which is CN. What would I need? Don't overthink this. Yeah, NaCN. Have to be pretty careful with this reaction because you're dealing with a poison, but this is normal SN2 chemistry. So we've seen this for quite a while. Really simple, easy way to make a nitrile. The other one we saw in our last reaction map was from amides. And we said we could do this using thionyl chloride, and this is our new method. So we'll use SOCl2, and whoops, you can convert this into a new carbon-nitrogen triple bond. What do you think the byproducts might be from this reaction? Yeah, that sulfur dioxide gas that we see anytime we use thionyl chloride, and then HCl. So let's take a look at this mechanism. It's a little bit different than what we've seen. So we said thionyl chloride's a really good electrophile. And in this case, what ends up happening is the oxygen on the carbonyl will attack in, not the nitrogen on the amide. So these will kick up electrons, and then the lone pair will attack in and kick up electrons here. And then in the next step, it's pretty similar to what we saw in the carboxylic acid mechanism. The oxygen will clamp down, kick off the chlorine, or chloride, I should say. And then your base will come along and deprotonate your nitrogen. Typically, like I said, these reactions are run using a non-nucleophilic base like pyridine or triethylamine. And now that you've got your carbon-nitrogen double bond, the nitrogen can clamp down, kick off our leaving group. And oftentimes this happens at the exact same time as a base deprotonating here. So let me actually draw out this bond, sorry. So the base can facilitate this reaction. So now we've got our nitrile.
So wait, is that step inserted?
Yeah, it's often shown as two steps, but usually people will show it as concerted just because it's really hard to protonate a nitrile, so it's believed that the base deprotonates it at the same time you're forming that triple bond. Oops. And then we've got this leaving group that got kicked off, which is very unstable. So after we form our desired product, this leaving group will quickly decompose and form SO2 gas, so sulfur dioxide, and Cl minus. So that's the thermodynamic driving force for this reaction, is the formation of sulfur dioxide gas. Does that make sense? Yep.
If we get to the product, would you want us to show that last step with the sulfur dioxide and also chlorine?
It's always a good idea to try to be thorough. I'm not going to be super picky. Yeah, I mean, we've seen this reaction so many times, you guys should be pretty familiar that that degrades into sulfur dioxide gas. All right, let's take a look at the reactivity of nitriles. One of them is hydrolysis. So we said if we have a nitrile, we can treat this with strong acid and heat, like we saw in the problem of the day from last week. And we go through this amide intermediate. However, if you've got enough acid around and you push it, you can actually convert this all the way to a carboxylic acid. So that's review from our problem of the day. Just like with amides, this can also be done under basic conditions. So if you treat this with NaOH and crank up the heat, followed by an acid workup, you can get to your carboxylic acid. And just like with amides, you really have to push these reactions. They typically don't fall apart very easily. The other cool reaction we can do with nitriles that we couldn't do with amides is we can treat them with organometallic reagents, specifically with Grignards. Let's see if we can try to figure out the mechanism of this. So let's say we've got our generic nitrile, and we've got RMGX. We know that the carbon is going to have a lot of negative character. The magnesium is going to be mostly positive. What do you think will happen? Will the R group with the negative charge attack the nitrogen end or the carbon end? Carbon. You can think of it almost like a carbonyl carbon. So the R group will attack here. Then we've got to kick up electrons to that nitrogen. So I'm going to call this R prime just to separate the two. Now we've got a double bond nitrogen with two lone pairs, which means it has a formal negative charge on it. Now that we've done that, we can't really add in any more Grignard reagents, right? Because if we tried to add in another Grignard reagent to that carbon, we'd have to kick up electrons onto that nitrogen, and it would be a -2 charge. That's not going to happen. It's too unstable. So at this point, you can start the quench for your reaction. So we'll treat this with our acid. The nitrogen will get protonated. And now we've got this imine intermediate, right? Pretty familiar with those from previous chapter. How can we convert the imine? Just treat it with a bunch of dilute acid, right? And then what do you think our final product will look like? It'll be a ketone, an aldehyde, ester, a penguin. Probably be a ketone, right? So if we look at the imine here, just replace that with a CO double bond. And so let's review the mechanism for this, just for practice. We know this nitrogen can get protonated. Now we've got water around. That's a really good nucleophile, at least when that nitrogen's protonated. Let me clean this up. And then we have our proton transfer, so I'll just do plus and minus H plus. We're going to move that proton over to the amine. Then our lone pairs will clamp down, kick off our ammonia. What's that? Oh, sorry. This should be NH3. Thank you. And then in this reaction, the ammonia that you kick off will act as your base and get you to a ketone. So it's one nice way to form ketones directly from an alkyl halide, is you can first turn it into a nitrile, and then just throw a Grignard reaction in to form your new ketone. So we haven't had that capability, at least in 2 steps. We had to go through more elaborate routes to get to our ketone, such as substituting it with an alcohol and then oxidizing it. All right, the last reaction of the chapter is reduction. So if we take our nitrile and we treat it with a strong hydride source like lithium aluminum hydride, followed by water, what do you think we might get out? It'll go to the amide, but what happens with amides when we've got excess LAH? It'll go all the way to the amine, yeah. So we'll overshoot this. It's hard to stop at the amide. And you'll end up with a primary amine. We're going to go back and cover amines a little bit later on, I think in May. But we'll have a whole chapter dedicated to amines where we'll review some of these reactions. All right, let's make a quick reaction map for nitriles. I know we covered a million reactions this chapter, but reaction maps are a good way of reviewing. So we said we could make nitriles from alkyl halides or amides. From an alkyl halide, we said we just needed sodium cyanide. And from amides, we saw the mechanism with thionyl chloride. So either one of those routes will work well. And then we can convert our nitriles to carboxylic acids, to ketones, or to amines. And we actually have 2 different routes to get to our carboxylic acid. Just like with amides, you can use acid and heat, or you can do base, heat, and then an acid workup. And with ketones, all we need to do is throw in a Grignard reagent. Oftentimes this is followed with a water workup. And then for reduction, we need lithium aluminum hydride in excess, followed by water. Make sense? I will tell you guys, last year my students got a little overwhelmed with this chapter just because there's a million reactions. The most important ones to review are the acid chloride reactions because that encompasses the most transformations that we covered this chapter. However, what I really recommend doing is trying to make some sort of giant reaction map. So we made mini ones here, but try to connect all of the mini reaction maps together. So I'll kind of show you guys what I mean. But this is an excellent way to review for the exam. Is start out with acid chlorides, which we know are the most reactive. Then have anhydrides. Then have esters. Then have amides. Then have nitriles. And somewhere around here, throw in a carboxylic acid for good measure. Your goal should be in your reaction map to add in as many arrows as humanly possible. What's that? Oh, sorry. This should be a carboxylic acid. You could throw in an aldehyde just for fun. But try to connect this with as many arrows as possible. And then when you're done, throw your reaction map away and then do it all over again. It seems tedious, but oftentimes just that process of mapping it out, connecting all the dots as many ways as possible is the best way to solidify these reactions. Oftentimes they're really repetitive, so it doesn't take too long, but just set aside a block of time and try to make your own reaction map. What I think we'll do at the last chunk of time is we still have like 5 minutes, so I'll let you guys actually work on the pod that's due tomorrow and class today, and I would recommend trying to work with some classmates in here. I'll walk around the room and try to help too.